Welcome back to our course on clean architecture. I'm Matthew Renzi with Pluralsight, and in this module, we'll learn about using an application layer in our architecture. As an overview of this module, first, we'll learn about architectures with an application layer and how this differs from a traditional three-layer architecture. Next, we'll learn about the dependency inversion principle and how we can use it to make our architecture more flexible and maintainable. Then, we'll evaluate the pros and cons of implementing an application layer. Finally, we'll see a demo where we'll walk through the code used to implement a command in the application layer of our demo application. Just to make sure we're all on the same page, what are layers? Layers are boundaries or vertical partitions of an application designed to represent different levels of abstraction, maintain the single responsibility principle, isolate developer roles and skills, help support multiple implementations, and assist with varying rates of change. Essentially, layers are the way that we slice an application into manageable units of complexity. Let's start with what we already know, the classic three-layer database-centric architecture. First, we have our user interface layer, which provides the user with an interface into the application. Next, we have our business layer, which contains the business logic of the application. Finally, we have our data access layer, which contains the logic to read and write to the database. This works just fine for simple CRUD applications, that is, applications that perform basic create, read, update, and delete operations on data within the database. However, it doesn't work all that well with complex or rich domain models. In addition, there's a lot of ambiguity about where application-level abstractions versus domain-level abstraction should go. This has led to the development of a more modern four-layer domain-centric architecture. First, we have our presentation layer, which provides the user with an interface into the application. Second, we have an application layer, which embeds the use cases of the application as executable code and abstractions. Third, we have a domain layer, which contains only the domain logic of the application. Fourth, we have the infrastructure layer. Oftentimes, it makes sense to divide this layer into one or more projects. For example, a common variation is to create a separate project for persistence and a separate project for the remaining infrastructure. For example, in this diagram, we have the persistence portion of the infrastructure layer, which provides the application with an interface to the database or other persistent storage. Then, we have the rest of the infrastructure layer, which provides the application with an interface to the operating system and other third-party components. Finally, we have our cross-cutting concerns, which are aspects of the application that cross all of the layers of the system. There are obviously a few variations on this architecture. For example, multiple user interfaces, adding a web service layer, separate projects for external dependencies, but the general structure is essentially the same. Here we have the application layer. It implements use cases as executable code. For example, a customer searches for a product, adds it to their cart, and pays with a credit card. We structure this executable use case code as high-level representations of application logic. For example, we might have a query that searches for a product for a customer, or a command that adds a product to their shopping cart. The application layer knows about the domain layer, that is, it has a dependency on the domain, but it does not know about the presentation, persistence, or infrastructure layers. That is, there are no dependencies on the outer layers of the application. The application layer, however, does contain interfaces for its dependencies that these respective outer layers then implement. Then we use an IOC framework, that is, an inversion of control framework, and dependency injection to wire up all the interfaces and their implementations at runtime. In addition to the dependency arrows in our diagram in orange, I've also added additional arrows in blue to indicate the flow of control through the application. We can follow the flow of control through the application from the users at the top of the diagram down to the database and operating system at the bottom of the diagram. In addition, we can follow the dependency arrows, which flow both upwards and downwards towards the domain. Now, some of you may be wondering if I've accidentally drawn two of these orange dependency arrows in this diagram upside down. Specifically, the arrow between the persistence project and the application project, and the arrow between the infrastructure project and the application project. Now, this is a completely reasonable assumption because it's probably quite different than what you've seen with the classic three-layer architecture. However, these inverted dependencies are in fact correct. When building this more modern architecture, we utilize the dependency inversion principle. It states that abstraction should not depend on details, rather, details should depend on abstractions. So, in the persistence and infrastructure layers, we implement the inversion of control pattern. That is, our dependencies oppose the flow of control in our application. This provides several benefits, such as providing independent deployability. That is, we can replace an implementation in production without affecting the abstraction that it depends upon. It also makes our architecture more flexible and maintainable as well. For example, we can swap out our persistence medium and infrastructure dependencies without having negative side effects ripple throughout both the application and domain layers. This is highly useful for agile applications where we often defer implementation decisions as late as possible when we have a much better understanding of the specific needs of our application and its implementations. This is a strategy referred to in agile software development as the last responsible moment, an idea which we'll talk more about in the last module of this course. Please also note that sometimes we need to add an additional dependency from the persistence project directly to the domain project when using an object relational mapper, that is an ORM. This is the dashed orange arrow in the diagram on the right. This is necessary for the ORM to map domain entities to tables in the database, since the persistence layer needs to know about the entities contained in the domain layer. Using an ORM is optional when creating clean architecture, but it can save a tremendous amount of development time and effort if used correctly. Here's a quick visual example to show how all of these classes and interfaces are all wired together in our demo application. We have our presentation project, application project, domain project, persistence project, infrastructure project, and our cross-cutting concerns project. In the presentation project, we have a sales controller that has a dependency on the iCreateSales command interface in the application project. The createSale command class in the application project implements this interface. This class contains the high-level application logic that fulfills the use case for creating a new sale. The class has a dependency on the iDatabase service interface and the iInventory service interface, both of which are contained in the application project as well. The database service class in the persistence project implements the iDatabase service interface, and the inventory service class in the infrastructure project implements the iInventory service interface. As we can see, all of the dependencies point towards the application and thus transitively towards the domain. All of the details, that is implementations, depend upon abstractions, which are interfaces, and we utilize inversion of control for both the persistence project's dependency on the application project and the infrastructure project's dependency on the application project as well. Our cross-cutting concerns are a bit different as there are typically multiple projects that all have dependencies upon them. For our cross-cutting concerns, we store both the interfaces and the implementations in the cross-cutting concerns project. For example, the iDate service interface and the date service class, which implements this interface, are both contained in the cross-cutting concerns project. This is because multiple projects need to reference the iDate service interface, so it must be contained in the cross-cutting concerns project referenced by all of the other projects. So why would we want to implement an application layer in our architecture? First, with an application layer, we're placing focus on the use cases of the system, which, as we've stated before, are essential to the primary inhabitants of the architecture, that is, the users. This provides us with the same benefits that we discussed in the first module of this course. Second, we embed our use cases as high-level executable code, which then delegate low-level steps to other classes. This makes it very easy to understand the code, the use case's intention, and to reason about the software as a whole. This is highly beneficial for developers creating the application and the developers maintaining the application. Third, it follows the dependency inversion principle, which, as we explained earlier, makes our code more flexible and maintainable. In addition, it allows us to defer implementation decisions until later in the project, and thus evolve the architecture over time. There are also several reasons why we might not want to implement an application layer. First, the primary reason is that there's an additional cost to creating and maintaining this layer. Layers in software architecture are expensive to create and maintain, so we generally want to keep the number of layers in our system as small as possible. Second, we need to spend extra time thinking about what belongs in the application layer versus what belongs in the domain layer, rather than just throwing it all in a business logic layer. Third, the inversion of control between the application layer and the infrastructure layer is often counterintuitive for novice developers. However, after you've wrapped your brain around it, it becomes quite a bit easier to reason about. So now let's take a look at how the application layer is implemented in our clean architecture demo. It's really important to note again that this demo application is the simplest application that I could create to demonstrate the basic concepts of this set of architectural patterns, practices, and principles. In addition, I've also stripped out other common aspects of modern software applications like validation, security, logging, event handlers, and much more. What's important right now is to capture the essence of these practices. Everything else will just get in the way of learning. However, I'll attempt to point you in the right direction to learn more about these other aspects of software architecture at the end of this course. Let's begin by taking a look at the application project. Again, we see that our folders correspond to the key entities, that is, the aggregate roots in our application. For example, customers, employees, products, and sales. These folders contain the commands, queries, and other application services that correspond to the use cases surrounding these key entities. In addition, we have a folder called Interfaces, which houses all of the interfaces, that is, the high-level abstractions, that represent the external dependencies contained in the presentation, persistence, and infrastructure projects. For example, the iDatabase service interface and the iInventory service interface. From the application project's point of view, it doesn't care how the low-level details of these dependencies are implemented. It is only concerned with the high-level abstract representations, that is, the interfaces that these dependencies will implement. It's up to each class that implements these interfaces, for example, the database service class and the inventory service class, to decide how they want to implement the low-level details. In order to follow the flow of control through the application, let's start with the Sales Controller class in the presentation layer. The Sales Controller class is an ASP.NET MVC controller that handles displaying web pages associated with the sales entities. It doesn't matter what type of presentation framework we're using, we could just as easily have used WinForms, WebForms, or built a simple console application, and the general concepts that we'll be demonstrating will be the same. What's important to note is that the Sales Controller class is using dependency injection via constructor injection to inject interfaces from the application project into itself. These interfaces provide an abstract representation of the commands and queries contained in the application project that the Sales Controller will use to complete its tasks. The Sales Controller then delegates the work to these commands and queries so that they can perform the appropriate work and either modify application state or return the results of the query. The Sales Controller isn't interested in knowing how any of this work is done, it's only concerned with how to present this information to the users. For example, the Sales Controller's index method simply executes the getSaleList query and displays the results as a view. The detail method executes the getSaleDetail query and returns a detail view. The create method returns a view that allows the user to enter the information necessary to create a new sale. It does this with the view model to hold the data necessary to create that sale. And the HTTP overload of the create method takes in that view model, filled with the data the user entered, and passes it into the create sale command as an argument, then redirects the user back to the index page. Now we'll look at the create sale command to see how this application logic is implemented. In the next module, we'll take a look at the two queries, that is the getSalesList query and the getSaleDetails query as well. First, let's start by looking at the iCreateSale command interface in the application project. This interface creates the method signature that the createSale command class will implement. We have just a single method called execute that takes a createSale model. This model will contain the data necessary to create a new sale. Next, let's take a look at the createSale model class in the application project. This class contains all of the data necessary to create a sale. As we saw previously, this object and its data will be passed from the Sales Controller into the execute method of the createSale command. Please note that this class is using the unique identifier for each related entity necessary to create a new sale, that is, customer ID, employee ID, and product ID. In addition, this class also contains data to represent the quantity of products sold. Now let's take a look at the createSale command class itself in the application project. First, the createSale command implements the iCreateSale command interface. This is necessary so that our dependency injection framework can inject this class in place of the interface at runtime. This way, the Sales Controller in the presentation layer, which uses the iCreateSale command interface, will be working directly with the createSale command class instead. The class contains definitions for 4 private read-only fields for each of our 4 dependencies. They are the iDate service, which provides us with current date and time information. This interface is implemented by the date service in the common project, which contains cross-cutting concerns. iDatabase service, which provides us with access to the database. This interface is implemented by the database service class in the persistence project. iSaleFactory, which creates a new sale entity given the necessary data. This interface is implemented by the SaleFactory class in the application project itself. And finally, the iInventory service, which provides us with an interface to the inventory service and allows us to communicate with the inventory system. This interface is implemented by the inventory service class in the infrastructure project. All 4 of these dependencies are injected into the constructor of this class via dependency injection. The execute method of the createSale command class takes a single argument, that is, a createSale model class, and returns void, that is, the command does not return anything to the Sales Controller. The logic for this command should read like high-level application logic, which delegates low-level implementation logic to the respective implementation classes. We start by getting a date using the getDate method of the date service. Next, we get a single customer from the customers repository in the database service that matches the customer ID in the createSale model class. Then, we get the matching employee from the employees repository and the matching product from the products repository. For clarity, we'll also create a variable called quantity to temporarily hold the data from our createSale model's quantity property. Now, we'll use a SaleFactory to create a new sale entity. Using a factory keeps the low-level details for how to create a sale out of our high-level application logic. In addition, it provides us with a seam in the code to make testing much easier, which we'll see in a later module. Now, we add the newly created sale to the sales repository contained in the database service class. Save the new record to the database, and notify the inventory system that a sale has occurred, passing it the unique identifier for the product that was sold and the quantity of products that were sold. The high-level application logic in this command represents the use case for creating a new sale. The code is very simple, straightforward, and easy to read and understand. In fact, it practically reads like instructions telling us exactly how to create a sale. Please note that there are more advanced design patterns for handling commands and command logic. For example, we could have used the Gang of 4 command object pattern, or the command handler pattern common in CQRS architectures instead. However, I'm attempting to keep things as simple as possible for this demo. Now let's take a look at some of the dependencies that our create_sale command depends upon. First, let's look at the iDatabase service interface. This interface is contained in the application project since it is a high-level application abstraction. It contains the application's interface to the database or other persistent stores using the repository pattern and the unit of work pattern. The repository pattern represents entities contained in a database table as a collection of domain objects using a simple collection-like interface. That is, it provides methods to add, get, and remove objects from the database, which in turn performs the appropriate create, read, update, and delete operations when the changes are saved to the database. The unit of work pattern maintains a list of domain objects affected by a command being executed in the application and coordinates the writing of these changes to the database. So, with these two patterns in place, we can access our customers, employees, products, and sales as if they were a collection of objects rather than deal with them like database tables. In addition, we have a save method, which is used to save changes to the database using the unit of work pattern. The iDatabase service interface is implemented by the database service class in the persistence project. This class inherits from DB_Context, which is a base class used by Microsoft Entity Framework to handle all of the low-level tasks to map domain objects to database records. All of the low-level code contained in this class is specific to Microsoft Entity Framework, and thus our application logic isn't concerned with any of these details. This means that we could swap this implementation out with another implementation without breaking any of the application or domain logic. For example, we could replace Entity Framework with another ORM like nhibernate, or just write our own JSON serializer implementation instead. However, because we're following the contract that the iDatabase service interface specifies, changing this implementation should ideally not cause any changes in the application or domain projects. I've chosen to use the IDBSet interface from Entity Framework in the iDatabase service interface to keep things simple for this course. IDBSet represents a collection of entities just like the repository pattern entails. However, it's an interface specific to Entity Framework. Using this interface directly isn't a very clean practice as it leaks the IDBSet abstraction from Entity Framework into our application layer. In addition, exposing all of the repositories and the save method in a single iDatabase service interface potentially violates the interface segregation principle. So if you'd like to see a much cleaner yet slightly more complex implementation, please see the following branch in my GitHub repository. This solution completely eliminates all application-level dependencies on Entity Framework as well as the iDatabase service interface. It does this by using a separate repository interface and corresponding class for each aggregate root entity to implement the repository pattern. In addition, it uses a standalone iUnit of work interface and corresponding class to implement the unit of work pattern. The remaining dependencies, that is, the date service, inventory service, and sales factory, look roughly the same as what we just saw with the database service dependency. They all use a C# interface to define the high-level application interface, encapsulate the low-level implementation details in a corresponding implementation class, and delegate the low-level implementation details to the corresponding class that implements the interface. The only real difference with the other three dependencies are the following. First, the inventory service class is contained in the infrastructure project since it doesn't specifically pertain to persistence. Second, both the iDate service interface and its corresponding date service class are both stored in the common project since the date service is a cross-cutting concern that can be used by all layers in the application. And third, the iSaleFactory interface and the SaleFactory class are both contained in the application project since the SaleFactory is an application-level service. I encourage you to take time to download the sample code and take a look at these other dependencies. Seeing multiple examples will really help you to solidify these ideas in your mind. We covered a lot of code in this demo in a short amount of time. If you had difficulty following along, I recommend that you spend some time becoming familiar with the sample code, and then I encourage you to watch the demo again to make sure that you fully grasp all of the concepts that we're discussing. If you've understood the concepts we've covered so far, the rest of the demos in this course should be relatively easy to follow along. If, however, you're having difficulty following the demos, it might be worth taking a bit of extra time to clear things up now before we move on to the next module. In this module, first, we learned about architectures with an application layer and how this differs from a traditional three-layer architecture. Next, we learned about the dependency inversion principle and how we can use it to make our architecture more flexible and maintainable. Then, we learned about the pros and cons of implementing an application layer. Finally, we saw a demo where we walk through the code used to implement a command in the application layer of our demo application. In the next module, we'll learn about command query responsibility separation in our architecture.